Today we're going to actually talk about a very interesting attack called a buffer overflow. Before we understand how these things work, and you need to understand a lot of things. Okay, so I like this buffer overflow because it involves a lot of knowledge. Okay, and you have to actually understand all this knowledge to be able to fully understand. Okay, many people they understand buffer overflow. You ask them what is buffer overflow, and they can explain that to you. But at the low level, they probably won't be able to do that. Okay, so I really want you to be able to explain that and from very low level. Okay, starting with the memory layout. Okay, so this is actually the memory layout. So when you run a program, okay, and this was actually your memory looks like for your process. Okay, it involves several regions. Okay, so the buffer overflow that we are talking about is going to be the stack-based buffer overflow. Okay, and that means the buffer is allocated on the stack. Okay, and they're actually the heap-based buffer overflow. So the buffer is allocated on the heap. The way to attack them are quite different. Okay, for this one is much simpler. Okay, for this one it's quite complicated. Okay, so in this class we're only going to focus on the stack-based. Okay, the heap-based buffer overflow, the idea are similar, just technically, and you have to overcome a lot of hurdles and to be able to make it work. Okay, so I don't want to get so complicated on that. So we're going to use the stack-based, and that's actually the most common one, the buffer on the stack. Okay, so and there are several regions. So now if this is the program, okay, this is the program. So now I'm going to ask you, I'm going to label some of them, and so I'm going to label this region. Okay, these are the. So I'm not going to label them. I'm going to label here. So for this variable, this is a global variable, and actually it's 1,100. Where will this variable be located? Take a guess. Okay. 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 Heap. That's good guess. Okay. PSS segment. Okay. That's good guess. Stack. Okay. So. Okay. Great. You are right. Yes. This is in the data segment. Okay. So the global variable or static variable. Okay. Global. Static. Okay, so this is also true for the static variable. Okay, so you can see there's a static variable. Okay, the global and the static variable, they need their location cannot be on the stack, because stack is during the execution of the function, the stack is effective. But global and static, they're going to be effective during the life cycle. Okay, so they can only be put on these two places. Okay, those variables are already defined. So either the BSS segment or data segment. The difference here is if the variable is already initialized. Okay, so here it's initialized. It's going to be put in the data segment. Okay, if the value is not initialized, it's going to be put in BSS. Okay, so here, so initialize in the data segment and not and in the BSS. So why do we separate them? Why can't we just put them together in the data segment? Why do we need to put the non-initialized one in a different segment? Why do we do this? There's got to be a reason, right? So if you do not specify, what are you going to get? If when you write this program, when y is not initialized, it's going to get 0. How come you get 0? Why? How can you get 0? Okay, because you are put in the BSS segment. When the OS create this BSS segment, it zero out everything inside, and that's why. So they don't want you to have arbitrary value for uninitialized the variable. They want you to start from 0. Okay, and that's why those variables will be put in BSS, and they will zero out everything in that segment. Data segment, so your variable is already initialized. They will not touch that. Okay, otherwise they're going to change the behavior of the program. So during the initialization, BSS segment is actually initialized with 0. Okay, and that's the main reason. Okay, why put in there. And so these are the basically the global variable or static variable that you created in the program. Now, let's look at this. These are local variable. Where will this be located? Okay, that's great. This will be on the stack. All the local variable, and they will be allocated on the stack. And we're going to actually give more details about that. Okay, so, and this is the type of variable that we are interested in the buffer overflow. Okay, and how about this variable, PTR? Where's this PTR allocated? This is a tricky question. Where's the PTR located? Where's this variable located? Stack. Still stack. This is a local variable, right? So PTR is still on the stack, but when we malloc, we're going to get a block of memory. Where's that block of memory located? That's going to be on the heap. Okay. So this part is going to be on the heap. Okay. But PTR itself is a local variable, and that one it will be on the stack. Okay, so this is what actually the memory layouts looks like. Okay, and these are all basically cover all different type of data, right? Local variable, static variable, global variable, and dynamically allocated memory. Okay, so this is what actually your memory looks like. Okay, so we are actually going to focus on the stack part and focus on local variable, but you need to know and those part and just. That's part of the OS actually. So another thing that a lot of students are confused is the virtual address versus physical address. Okay. So let me just explain this a little bit. If you have taken an OS class and you probably are very clear about physical address has to be unique. Okay. That's actually your physical RAM. If I'm using this address and you cannot use. Okay, if my process is using this one, if you are using that, then we're going to have a conflict. Okay, unless this is shared memory. Okay, so, but when we actually talk about the memory address in the process, we're talking about the virtual address. Okay, so every process they have its own virtual address. So this process 1, P1, P2, I may have this address 5000, 0x5000. And you may also have 0x5000. So I'm using 5000 in my program. You are using 5000 in your program. We are not talking about the same physical address. It's just virtually we have the same. Okay? So there's actually a mapping to map this virtual address to the physical address. That is done by the OS, either through the page table or through the segmentation. So this will go through the translation, and eventually it's going to be mapped to one block here. So the actual physical address could be some other number. Okay, so this is just virtual. And here the same thing, and you're going to actually, this block is going to actually go through the translation, okay, and then go to this block. So you get this block. So although we are using the exact same virtual address, but physically they are different. Okay, so that's some students got confused, and how come you use 5000? I'm using 5000. Why wouldn't it be a problem? Okay, this is because these days we're all using virtual address. Okay, so I can basically from 0 to 4G. Okay, if I 32-bit machine, I can claim I own the 0 to 4G. Okay, and you can claim the same thing, and 0 to 4G, and that's your virtual address space. Okay, so the address, if you say I'm going to use this address, if this block is not a map to a physical address, although this virtual address does exist, there's no physical memory mapped to that. Okay, so this is an invalid address. If you try to fetch something from here, right? You say, oh, I'm going to do the 0x1000. But this one doesn't map to any physical address. And then the instruction to get data from here will actually cause your program to crash, because that's an invalid address. Okay, CPU is going to say, no, you have not mapped to any physical. There's nothing here. Okay, and the CPU is going to raise a fault. And that fault is going to trigger the OS to kill the process. Okay? So basically you can access anything there, but only in the place where you have a physically mapped to a memory, that's the real address. Otherwise, all the other ones, they're not real. Okay. So let's look at the stack layout. Okay, we're going to focus on the stack, and let's look at what stack looks like. And in particular, let's look at a function. Okay, stack is mostly used for function. So when you make a function call and local variable argument, they are located on the stack. So let's take a look at what a stack looks like. So here's a function, very simple function. So I have a function, I have two arguments A and B. I'm also just using integer to make it simple. I have x and y, I have this simple things. Now, when somebody called a function, when the function is called, let's see, fun, we're going to put 5 and 6. When you call this one, okay, and then this in your code, it looks like you just call this, but the compiled code, the binary, okay, and it's going to actually start pushing information into the stack, okay. So, and according to the layout of the stack frame, this is called the stack frame. So your program will create a frame for this function. Okay, this frame is going to use to contain the local variable argument, okay, as well as several other things which we're going to talk about. So first it's going to push in data into the stack. So right now here at the beginning the stack point is here. Okay, that's before we actually push. Stack grows from high address to low. Okay, so this is the high address. So stack basically grows the upside down. Okay, so and then first it's going to actually push B into that. Okay, we're going to explain why B first. Why not A, right? Because naturally you would push A first, right? And how come we push B? Okay, later on I'll explain that. So B is going to be pushed into first, and then next one is A. So B is going to 6 is going to be pushed into here, and then 5 is going to push in here. Okay, and then the next two positions are very critical. Okay, one is used to return address. So return address is going to be pushed into here. Return address basically is the instruction following my current invocation. So if I'm calling this, then whatever is the following instruction, okay, the address of this one will be pushed into the return address. Okay, so now the next one is the previous frame pointer I will talk about later. Okay, and after that, so these are this argument and these two data. Now after that, it's going to allocate a block of memory for local variable. Okay, so now the local variable, and I have x and y, I have two local variables. Okay, but the order of this one, there's no actually the specific order. You can put x before y, y before x. It doesn't matter. So, and the compiler will make that decision. Okay, some compiler may choose put y first, put x. Okay, as long as the compiler knows which one is which, and you won't have a problem. So you shouldn't assume any order, and also you shouldn't assume the space allocated for here will be 8 bytes. Okay, assuming each integer is 4 bytes, you would think I will have 8 bytes here. Okay, compiler may add some gaps in between. Okay, and for various reasons. Okay, so this part, all you need to know is that they contain the local variable. Okay, in which order, how much space, is really depending on the compiler. But this part is fixed. Okay, this is an architecture issue. You cannot change this part. If you change this part, it's going to mess up the system. Okay, this has to be the return address. This has to be the previous frame pointer. Okay, this is decided by the architecture. Okay. So one thing we need to know is inside of our program. Let's see here. I need to add A and B. I need to put it in X. So I need to compile this into binary, right? When I compile into binary, I need to know the address of A and B. How do I know the address of A and B? when I generate to the binary code, I got to put something in my instruction so I can know where to fetch A, where to fetch B. But I'm doing the compilation stage. I don't even know where this program is going to actually run. How do I know that address?
It can be in a form of offset.
Offset of what?
Of the first address which is allocated to the program.
Offset of the
program memory which is allocated to the program.
Okay, offset of something, right? Okay, so yeah, offset of something. That means that offset cannot change during the wrong time, right? So if this offset changes during the wrong time, they're going to mess up that offset. So the base is very important. Okay, so that's very good. So I don't know the absolute address. That's for sure. Forget about the absolute address, because when I run this, I don't know where the stack start. Different OS, they're probably going to start from a different place. Okay, and so I cannot use this one as a base. Okay, so but what should I use as a base? Offset is good. We need to use offset. We just need to find a base point. Okay, and that's where this frame pointer is introduced. Okay, frame point to a fixed place on the stack. Okay, so always point to here. Point to this previous frame pointer field. And this is so in the x86, there's a register called EBP. That's actually the base pointer. Okay, so when you make a function call, this EBP is always going to point to this position. Okay, and that's decided by the architecture. Okay, so now once you have this one, you know this will always point to here. Now this will solve the problem, right? Now we know A. What is A's address? EBP plus 4 bytes for each. Plus 4 is going to get here, right? Plus another 4 is going to be A. So EBP plus A is going to be A's address. Now EBP plus 12 is going to be B's address, right? Now you can understand why B is pushed first, right? Because you want this number to be lower, right? A is at the beginning. This number has to be lower than B's number, because A is the first one. Yes, question.
How much is each box?
We are assuming a 32-bit machine. Okay, 32-bit machine. That's each box return address. This one, they are all 4 bytes. Yeah, including the value, integer, they are all 4 bytes. Okay, when you work on our lab, you are using 32-bit machine. Although your real machine is 64-bit. Okay, your real machine these days, they are all 64-bit machine. But when we build our virtual machine, we choose the 32-bit. Okay, so instead of that, you should use the 32-bit to calculate. Okay, so and now x1. Right now, I just put x right below that, but x can have a gap here. Okay, so x, if it's right behind this, that would be the EBP minus 4. Should be minus 4, right? Okay, so that's actually how inside of your code, and your code specify the address using the stack. Okay, and this is actually the binary code for the assembly code for x equal to a plus b. If you look at this, I'm moving the EBP. This means EBP plus 12 into EAX, right? I'm moving B's value, right? That's B's value into EAX. I'm moving the EBP plus 8 to EDX. So I'm moving A's value into EDX, right? I'm adding them together. And the value will be saved to EAX. So that's the sum of these two. Then I'm moving EAX to EBP minus 8. Okay? And that's actually its X value. And you can see X value here is not right below this, right? It's actually EBP minus 8, because there's a gap. As I mentioned, in this diagram, I draw X right below that. And because the X is the first parameter, the local variable. But in reality, okay, and compiler may add some gap. But the compiler knows if they add a gap, they know where x is, where y is, as long as this number is actually modified accordingly. So compiler will not be confused. Okay, so just don't assume x is always going to be -4, y is going to be -8. Okay, this example shows you it's not the case. But this is always the case. Okay, because when you write a function, okay, if you do not follow the standard, and when I call you, I'm going to have trouble, right? So if you write a function for yourself, and that you're okay, you're self-contained. But if you have write a library function, and you put A before B, and now when I actually compile my code, when I need to push A and B, and I don't know the order, I'm going to follow the standard order. I'm pushing B first, pushing A first. But you're saying I'm actually swap that. And you cannot do that. Okay? Your local variable, I don't care, because I don't even see your local variable. It's yours. You can put it in any order you want. But argument you can't. Argument is meant for other people to call. Right? Everybody has to follow standard. Okay? Okay, so that's pretty much the layout of the stack. Okay. Now, if you're calling a function from main function, you are calling. So let's say I'm calling from main function. I'm calling the foo. From foo, I'm calling bar. Okay. So I will have a main function in the stack. Okay, and then inside of main function, I'm going to call foo. Then another stack is going to be created. And then inside the foo, I'm called bar, and then bar, the stack is going to be created. Okay. The problem is I only have one EBP. So initially, when I'm here, EBP point to here, right? When I call foo, EBP has to be point to here, and I lost that position. I only have one register to store that. Okay. So that's why you need to remember that. Okay, if you actually change the EBP and move to here to point to your kind of frame, you need to remember what is the previous frame. And that's what this previous frame pointer is for. You store that one, so this one remember the previous one. Okay, and same thing, when you move the EBP to here, this one remember the previous one. Okay, now we return. Okay, now we say, okay, bar returns. Return is going to reverse that. Return is going to be moved the stack pointer to here. That means this whole thing is going to free up. Okay. Now this space is taken back. Whatever is in there, the information may still be there, but other function call will use that. Okay. Information, you can see the information there get lost. That's the intention. I create a stack. When I return, I revoke the stack. Okay. And also I need to change my EBP back to here, because EBP right now is put in here. So before I return, I'm going to get out of this information. I'm going to use that to actually change my EBP. So my EBP is here. And now I'm in a foo. I have my EBP. I have my offset, so I can access all the local variables there. Okay. And so when I return to main, okay, the same thing, the stack pointer point to there, and EBP is going to be updated to point to here. And this whole thing, and now it's going to be free. Okay? And that's how this the function call works. If you have a recursive call, right, if you are inside a foo, okay, and you have this, you call foo again, okay, and every time you call your foo, a new frame is going to create it. So on this stack, so you're going to have a lot of frames created for the foo function. Each of them has its own local variable, okay, and its own argument. They will not actually be the same. Okay, so but every time you return, and it's going to actually roll back. Okay. Okay, so now as you understand how the stack works, okay, the layout, the arrangement. Okay. So now let's look at if I want to copy data to buffer. Okay, and buffer overflow is caused by the overflow of buffer, and that is related to the copy, data copy. If I don't copy data, I don't overflow a buffer. Okay? So here, I have a string, okay, I put a 0, okay, so if you're not familiar with when in the C program, you put /0, that's different from just putting a 0 in there, okay, inside a string. If you, inside a string, you said I have a 0, this 0 is actually character 0, okay. Inside the array, this 0 is going to be replaced by a number, okay, and that's going to be ASCII value of this 0, okay, and that's actually 0x30. So that's ASCII value of 0. So if you put a 0 in this inside of your memory, actually 30 is actually put in the memory. Okay? But if you inside your C code, if you put a /0, and you are telling the compiler, don't convert this 0 to the ASCII. I want a 0 here. Okay? So inside the memory, then 0 is going to be put inside the 0. Okay? That's how you actually tell the compiler not convert that data. I just want a binary 0. Okay. Anytime you want to put a binary, you said I want to put a binary 8, you /8. And compiler knows, okay, this is not ASCII 8. I should not replace this with 0x38. I should just put 8 there. Okay? So, and there are many different functions to copy the data. Okay? So usually when you copy the data, you have a source and you have destination. And you copy the data from source to destination. Okay, and this happens very, very often. Okay, and usually the source is a buffer, the destination is a buffer. Okay, copy from one buffer to the other. Okay, and there are many ways to do the copy. So string copy is one of the common library function. Okay, string copy the string, assuming this is a string, copy this string to the other. Okay, and then there are the string cat, and the concatenation is also copying. Okay, so I want to concatenate this with another string. Okay, so and there are also memory copy, CPY. So memory copy, I'm not assuming this is a string. I'm copying this block of memory to another block. Okay, so memory copy you need to provide a size. Okay, because you are treating this as a binary value. Okay, and you need to tell how long. String copy, you don't specify a size. But how can the string copy end? How does string copy knows I'm done with the copy? Yes, says 0. Okay, string copy look at the 0. 0 marks the end of string. Okay, in here I did not actually put you don't put the 0 here. But when the compiler put this string, convert them to ASCII value, put in the memory, and it will automatically add a /0 at the end. All the string, they're going to end with /0. Okay? So when you write this, and you actually put a 0 in there. Okay? The length of this string should be the length of all this character plus 1. Okay? So don't forget that 0, and that's added by the compiler. Okay? So string copy will look at that 0. When you see the 0, it stops. Okay? And that's why you don't actually put the size. When I do this one, I put a 0 in the middle, and the string copy will actually stop here. Yeah, it will stop here because it says 0, right? So it doesn't care the string copy doesn't know when the string start and end. In my code, I want it to end here. I put some 0 in here, but string copy is going to stop in there. Okay, if I remove that 0, it's going to stop in here, and that's usual. Okay. So that's why there's no size here, no size. And that's where the problem is. If you do not specify the size, okay, and it's easier to make a mistake. Okay, because now the size is decided by the input. Okay, if I don't put 0 in there, okay, you may be able to copy a lot of data. Okay, so we are using the string copy as an example in our lab and in my lecture, but buffer flow not only happens in string copy. Okay, it happens in all sort of the buffer copy, including the memory copy. Okay, it happens. So just keep that in mind. Now let me just give you an example and a little bit more complicated. So here I have a string, and the content of this, I put just this definitely longer than 12. Okay, so the size of this is more than 12. Okay, and the buffer is 12 size. You can see I define this buffer as a local variable. That means this buffer is located on the stack. Okay? And so at least the 12 active bytes is going to be allocated for this buffer. And then I'm calling this foo, and I'm going to send this string to this foo. Inside of the foo, it's going to do the string copy. Okay? String copy is going to copy all my entire string until it says 0 at the end. And you can count this is definitely more than 12. And that's going to overflow that buffer. Okay? Some language, they will detect that. Some language, especially strong typed language like Java. If you write a Java program, if you overflow a buffer, Java is going to say, hey, you exceed the boundary. Right? That's because Java, you do not run directly on CPU. Your code is Java bytecode. You have a virtual machine, Java virtual machine, which interpret this bytecode. And that's how they can detect the violation. Okay? C code compiled directly to the binary that runs on CPU. Nobody's checking that. CPU doesn't know where's the boundary. Okay? So it will let you copy. So we'll start from here. You start from here, it's going to let you copy your buffer. And once you reach this, and CPU doesn't know, it actually gets to the boundary. Because CPU doesn't know your buffer is 12. Once you compile this into binary, all this information get lost. Okay? All the size information get lost. So it will keep compiling, copying to here until it is finished. Okay? So that means the previous frame pointer is going to be overwritten. The return address will be overwritten. Okay? And as well as the many other things will be overwritten. So then what's going to be the consequence? So tell me the consequence. What could be the consequence when I overflow this and I overflow this here? So remember, there's some gap in here. Could be a gap. Okay, I didn't draw them. So this one. But very likely these two will be overwritten. Let's see. Let's focus on this one. If the return address is overwritten, and what's going to be consequence?
Overwrites the current content of the address.
So remember, this return address points to whatever is below this, right? The instruction basically is going to be returned now, right? So now this is going to overwritten, and by something in your string. So right. So let's just consider this is just some random address now, right? Because it's actually the string value turns into the address. So it's got some random address. So when you return, it's going to fetch the return address, right? Jump. That's what the return does. Okay? So it's going to jump to this random address. Okay, now what's going to happen? Why is it going to crash? There's an address here.
It will try to fetch instructions from the address.
Okay, it's going to fetch the instruction. It will fetch, it's an address, right? It will fetch the instruction from there and go start to execute that instruction, right? So, and what's going to happen?
We're not guaranteed it exists, so it's going to crash.
What is not exist?
The address.
The address, very good. So first one, as I said, this address, let's say this address is 067,000, right? That's a virtual address. Okay, you're trying to fetch instruction from 7,000. But CPU says, no, this address is not mapped to a physical address. There's nothing there, right? And CPU is going to actually raise the fault, okay, because CPU doesn't know what to do. You're trying to fetch something from nowhere, right? So CPU is going to raise the fault, and it's going to kill the process. So it crash. So the address doesn't exist. It's not mapped, okay? So I should say it's not mapped. Crash. What else? So now address exists. Okay, it is mapped. Okay, something is there, right? And what's going to happen? So it's going to fetch something from there, right, and execute, right? What's going to happen at that moment? So it jumps to somewhere. Okay, jump to somewhere. Okay, jump to somewhere. There's an instruction. There's some data here. I'm not saying that's instruction. There's something there. Okay, I'm not guaranteed that's instruction.
If it's a very secure part of the memory, then you consider it at least.
Very good. So this could be a protected region. This could be a kernel address. And you're trying to jump to the kernel region. And that's hardware protection prevent you from jump into the kernel. Kernel is protected. Okay? And later on, in the later part of this semester, I will talk about that kernel level protection. You cannot jump to the kernel address space. That's protected by the hardware. Okay? So that will crash. So jump to protected place. Crash. Same thing. CPU says you're not allowed. I'm not gonna raise a fault. Okay? And then CPU, the OS is gonna kill the process. Okay? What else? What if this is not protected? This is yours. It's not protected area, and it exists. You want to jump into here. What could happen? You're going to fetch something. You're going to start execute.
If it jumps to an instruction that's placed there specifically by an attacker, then they can take control of the program.
Okay, that's one thing. Okay, let's say there's no attack here. You just jump to a random place. So this may not even be an instruction, right? Yeah. Instruction need to follow a certain format. This is just a random place. And this could be just data in there. This is just 0 in there. I don't know whether 0 is an instruction or not. So you're trying to get this 0 and you're going to run. CPU knows. CPU said, no, I don't know how to run this instruction. It's not an instruction. Okay? So this is invalid instruction. So you can see, you see that the program get crashed, right? These are the 3 reasons. Okay? And they're all different. Okay? And of course, you have to read the report and the code down to be able to learn what is the real reason. But these are the one of 3 reasons. Okay? And then if this instruction is valid, okay, and so that be executed, and then after that is executed, go to executing the another one, right? If this actually is indeed a code, and you would actually run this code, right? But it's different from your original code, and so at some point your program will have a trouble, and this is actually the most nasty actually error you will ever encounter. So because your code is running, but your results are different, right? And you look at the debugging, you say everything's right. Just simply you actually overflow this return address. You jump to some other code. And of course, you are not debugging that code. You don't even know that actual code exists. So sometimes if you're unlucky and you buffer for little here, and if it crashes, that's great. And I like my code can crash, because if it crash, it tells you where the error is. You can immediately go there and find the problem. But when this happens, and eventually your program crash, but it's going to be 100 seconds later, and you don't know exactly what goes wrong. Okay? So although this is not very common, but if you're unlucky and you get into this situation, it's going to take you a while to figure out and that this buffer overflow caused the program to crash 100 seconds later. Okay, so okay, that's how the buffer overflow actually, if you overflow buffer, this is what the problem is going to happen. Okay, one of them. Now, as attacker, okay, now so which one do you want? Which one do you want? So the last one I didn't write this down. Actually, wrong. Other code. Now, if you know that this is going to be the consequence, although right now we didn't put any control, right? We didn't do anything, but I observed that program, if overflow the buffer, it can achieve one of these things. Now, if this is the privileged code, and you're attacker, which scenario do you like? You like this one, right? So you're not interested in just crashing the program, right? You are really interested in that this program can run other code, right? That's what you're interested in. Right now, this other code you have no control. What if I have a control of that code? What if I let this program to jump to my code, right? That's going to be interesting, right? And then I'm going to write my code, and I'm going to let it jump to my code, and I can do damage, right? So that's what we want to do. So let's see. So let me see. Yeah. So yeah, I will skip the exercise part. So let's just look at this together. Okay. So I have a buffer overflow. Okay. So I know I'm going to control the input. Input is what I'm controlling. So you are controlling what is copied in here. Let me just write this. This is the buffer you're constructing. the source buffer, this is the source buffer. Okay, whatever the information you provide is going to go to the source buffer. The source buffer is going to be used to copy into this destination buffer. And obviously we make this large enough. So it's going to overflow all of this. Okay, and we know we're going to overflow the return address. And I know this is why if I put something here, so I'm going to put something here, a value to overflow this. In my previous example, I'm just putting some string value, right, random stuff. So that's why I cannot control what the consequence is. It may crash. But now I need to control the value. Okay, I cannot put a random value. I need to put a good value in there. My goal is to let this jump to my code. That's the goal. I don't want it to jump to a non-existent place. I don't want it to jump to the kernel protected space. I don't want it to jump to a non-instruction. I want it to jump to my code. But first you got to put your code in the memory. How do you put your code in memory? So first we got to solve this problem, how to inject our code. Let's see, malicious code. We are malicious. So we want this jump to my code. Let's forget about how to jump to that. Let's just see, how do I put my code into this, into the memory? The code has to be in the memory. Otherwise, it won't run. Okay? So how do I get my code in the memory?
Have the user download it off the
No, this is a privileged program. Let's see, this is a set UID program. I cannot change the behavior of this program. This program is running, when I'm running this, I'm a robot. The only thing I can control is the input that I provide to this. So this program asks for the input. So I'm going to provide this input. This input will be copied into the buffer. Okay, I cannot change its instruction. The only control I have is this input. Okay, remember, anytime when a set UID program asks for input, that's attack surface, and that's the surface we're using. Okay, so now, how do I use this input to inject my code into the memory?
Put it in the buffer.
Very good. I can put in the buffer, right? So whatever I put in the buffer will be copied in here, right? What if I just put in the high end of this, so I don't put my code to overflow the return address? I just put in here, right? And when you copy it, this part is going to be copied. So my code is going to be copied in here. If I can put my code in this buffer that is fit into the program, when the buffer overflow happens, this code will be there, right? So that solves my problem. I can inject my code, okay? Because you're asking me to provide your input, and you actually copy my input into your memory, okay? Therefore, my code is in there. Yeah, later on we're going to actually show you how to put the code in there. This is just instruction code, binary. We're going to write a binary code, okay? So you're going to put some binary data in here, not your C code, okay? So got to be a binary code, okay, machine code, okay? But we have that code. In the lab, we have already written the machine code for you, so you don't need to write that. I will explain how the code was written, but you don't need to actually write the code yourself. So that's first thing. So we got to jump to here. Now the second thing is, now my code is in here. Now I need to jump to here, right? And what does that mean? So that means I need to override this address, right? Override this region, right? With the address that points to the starting point of my malicious code, right? And so there's address here. I need to know what that address is, and doing the attack. How do I find this address? So I need to put this address, this number, into here. So when you do the copy, now this one is going to be copied into here. And this has to be in my input. So I need to put that address. I need to know. When I construct this input, and I assume eventually this input is going to copy into here, it's going to be in somewhere. I need that address. Without that address, I cannot override this return address. So how do I get that address?
These pointer.
From attacker's point of view, because this attacker is constructing this input. The program asks the attacker, give me that input. I'm writing the program, I'm running the program. At this point, I need your input. So this is the input that I get from you. Okay? So you need to construct that input. And so it can actually cause that damage. Yes?
We are the one who constructed that input, right? So we
Yes.
are knowing after how many bytes we have put that code.
So you are using the offset?
Yeah.
In the return address, do you put offset or do you put absolute value? In the return address,
Absolute value.
has to be absolute address, cannot be the offset.
We'll have calculation.
So this offset, let's say this offset is 100. You cannot put 100 in here. That's got to be the absolute address. So the question is, how do I find that absolute address? Cannot be this offset. Can you say it again?
Multiply by 4 and then add it. Because 4 is the number of bytes, so the number of blocks we have to go up.
But how do you know? So you don't even know you don't even know this address either. You don't know any of this address. As long as you know one of these addresses, you're okay because this offset is going to help you. But you cannot. Can you read the EBP value? You can't because setUID program is running with its own code. You have no control of the behavior. You cannot ask setUID print out an EBP for me, so I can use it. I know the EBP pointer here. I know that, okay? But setUID doesn't give you the value of EBPs, so you don't know what is in the EBP. And setUID doesn't even print out anything up here. If the program print out any address on the stack, I can guess, right? I can use the offset. I can calculate that. But setUID is not print out any address here. I don't know the actual starting point of this stack. So what do I do? When you run out of choice, what do you do? Brute force, very good. When you run out of choice, you guess. So you brute force, you guess. Okay? So let's guess. Let's guess what the address is. Okay? Now, what is the range of my guess? How random is this address? How random? So when the program starts, okay, and it's going to allocate the stack starting from some point, right? So now the starting point. If the starting point of this stack is known at the beginning of the execution, so how difficult is it for me to guess this address? What is the range? So I know when the program gets started, when the main function gets started, and assuming I know the starting point of the stack, okay, and I also know this stack, this frame, is going to be allocated somewhere here, right? So somewhere inside of a stack, and I don't know actually the distance here, okay, because this can be very dynamic, depending on when this function is called. But I know this one. If I want to do the brute force, how much try do I need to make? How many tries?
How many times you have called the variable, the second variable? Okay.
How
So you keep track of how many times you have used the memory. And how much of the code has used that?
Okay, how many records have been used? Okay, so we need to know how many records have been used. So in reality, so remember, if you have a 5 record, what does that mean? You have A equal B, B equals C, C equals D, D equals E, right? If A equals B, come back, A equals C, come back, A equal E come back, how many layers do I have? How? 2, right? So this the size of this depends on how many function call that you have on this call chain. Right? Anytime I return, I remove one. So if I have a recursive call, I will have it go very deep, right?
But at the same time, all that program is a software on the computer using that same memory.
No, every process has its own stack, virtual memory, its own stack, right? That's why it's different, right? You have your own stack, and no other process is going to use its own stack. They don't mix. Okay, so how many? So this value depending on how deep this call is, right? So how many of you like to write recursive function? How many of you like that? I don't like that, right? So most of the program you see, they are not recursive. Okay, when you take algorithm class, yes, there are a lot of recursive, but other than that, you don't see a lot of recursive. And what does that mean? That means this is not going to be very deep. The usage of the stack is not going to go to 100 levels deep, right? Only people taking algorithm class are going to do that, right? Otherwise, maybe a 5 level, 7 level, and yeah, depending on how complicated the program is. So that means this is shallow. Your stack is quite shallow, okay? So if you know this address and you know this is shallow, you don't need to guess it many times. Okay, so you can do the brute force. Okay, although the entire search space is 2 to the 32, right? That's a 32-bit machine. But if this is not shallow, maybe you guess 1,000 times, maybe should be sufficient. Try 1,000 times. Okay, you don't do that by hand, right? You are laughing. You assume you are doing it by hand. No, don't do it by hand, right? Write a script doing that. So do that. Okay, so that's so you just guess. Okay, the fact that this is this shallow, and also the fact that this is starting points of is fixed. And in the later on, they actually put some randomness here. Okay, we're going to talk about it later on. Actually, that's one of the countermeasures. They randomize the starting point, but before they actually put a randomness in here, the starting point is always a fixed position. Okay, because OS doesn't want to be so complicated, right? Every time I allocate a stack, why should I randomize my starting point? I will have a constant, right? Start from here. It's a virtual space. Everybody starts from the same virtual space. It doesn't matter, right? So that was the case. Always starting with a fixed position, and you're gonna see that your stack is really not shallow. Guessing is not so difficult. Now, what if you want to make it better? You want my guess, so even though 1,000 times and still too much, I want to make my life easier. So I can actually, even if I guess wrong, I can still be successful. So even if I guess I didn't hit this point, right? My address, I may be able to hit this point, hit this point, hit this point, hit this point. I still want to be successful. I have a very near miss, but I want to be successful. What should I do?
We can have kind of indicators in our buffer source which we inject. Like,
what do you mean indicator?
Like some values which we'll have a record of. Like if we hit the middle of that, then we know that this is like below my code, or like that.
So if I hit the wrong place, and my program will crash. So that's one try. I fail. Okay, because if you jump to here, as I said, this may not be an instruction, right? It's just a data, and you crash. Yeah, that's one try, and that's how you know you guess wrong. Try another time. Okay, but I want to hit this place, although it's not the beginning of my code. I still want to be successful. So what do you do?
Put instructions.
What instruction? I want to put instruction.
Return the address.
So he's right. So I need to put instruction. So I don't want it to crash. I got to put a valid instruction. But I don't want this instruction to obvious thing, right? So what instruction should I put in here so I can eventually get here? Jump. Jump. If you do the jump, you need to know jump to where. You need to have the address. We're getting the address. So there's a special instruction called no op. Basically, just allows you to go to the next instruction.
Yeah.
So you just put a no op. In the x86 is 0x80, no, 0x90. So basically no op. Okay, that's special the instruction, and what it does is does nothing, but to go to the next instruction. That's what it does. So you just pre-fill all your entire buffer with no op. Okay, so the entire thing is no op, and now it doesn't matter where you hit. Eventually, it's going to lead you to the engine point of your the code. Okay, so no op is part of our code basically. Yeah, so that's make your life easier. Okay, and actually in the lab we are actually teaching you. You can even do some investigation. So this code that we are running, I can make a copy of this code. I'm going to run that, of course, without privilege, because when I copy that, I lose privilege. But I'm going to debug this program. I'm going to actually look at where this is. Because when I run this program, and with setuid or without setuid, their memory will be identical. It's the same code. If I provide the same input, the memory location is going to be identical. So you can basically debug this program, and you're going to see where this buffer is, right? Where this return address. Where you just print out the EBP. That's enough. And when you just set a breakpoint, okay? And at that point, you said print out the EBP, and you get the EBP value. Now, if you run the setuid version, okay, and this value will be identical, okay? So of course, later on, there's some countermeasure placed. So in the lab, you have to read in the beginning part. In the lab, at the beginning, we have to turn off the several countermeasure. Okay, this is such a bad problem in the Linux OS. So over the last many years, a lot of countermeasure was developed inside of a compiler, inside of OS. So when you compile this, you have to turn on this special flag. Those flags allows you to turn off the countermeasure. Okay, and also you have to configure the OS to turn off the countermeasure, and then you can do the attack. Okay, and later on, the task 2, basically we're asking you to turn back on those countermeasure, and some of the countermeasure can be defeated. So you're gonna show how you can defeat the countermeasure. Okay, and then there's another countermeasure which we have another lab called the return to libc, because to defeat that countermeasure is not that easy. It takes another lab. So that's actually the concept, okay, and how the buffer overflow works, okay, and we actually understand some of this. But there's still several challenges we haven't talked about. So we have solved this problem. How do I inject the code? We've talked about how do I guess that, okay, and there's one more thing. How do I write this code, right? In the lab, you will not write this. I give that to you, but I want you to understand what we wrote. Okay, so this particular code, there's a name for this code. And so tell me what you want to do in this code. If this setuid program, what do you want to run inside this code? You want to run the shell, right? And so you need to write a shell program to execute the shell. In the code, what you want to do is you want to do the exec v /bin/shell. And you just want to exec v shell. That's what you want. But how do I write that code? In C, I can write in C. Okay, I can compile it in binary. Okay, but next class we're going to show you that that's not the way to write it. Okay, and there's so many other things that make this not work. You have to write this by hand and in assembly. Okay, so we're going to show you assembly version of that. There's actually writing this code is not very simple. It's very tricky. And takes a lot of skills. Okay, there's several things you have to overcome. Okay, so and there are competition on this. Who can write the shortest code? This is called the shellcode. There's competition. People compete for the writing the shortest one. Okay, I think the version we had in the lab may not be the shortest. It's about 20 bytes. I'm sure somebody can write even less. Okay, so that's I will show you how that code works and how they solve some of the challenge. Okay, and it's very interesting to learn the skill they use, and maybe something you can use somewhere. Yeah, but so I'm not requiring you to write that code. Okay, but to know that would be great. Okay. Okay, that's good. So next class, I'm going to continue to talk about the buffer flow, and then you can start working on the lab. Okay.